Hello, this is video's a hard probability paradox, but it's spurred on by a video from Wrath of Math. So he presented an insanely hard probability paradox, and that's what spurred this video on. His problem was you throw a die until you get a 6. What is the expected number of throws conditioned on the event that all the throws were even? And he took a poll and everybody guessed, and the majority guessed wrong, some guessed right. And the answer is 1/5 and 1.5, 1.5 rolls on average until you get a 6 conditioned on all the rolls are even. And that seems a little low since there's 3 even numbers. One of them's a 6, so there's a 1/3 probability of rolling a 6, assuming that's your sample space. And so you'd expect at least 3 rolls, but it's 1.5, and that's pretty counterintuitive. Now, the problem that intrigued me, the paradox that intrigued me, is what's the probability that n is 1, that you roll a 6 on the first die or the first try, given that you're rolling all evens? People, I think it seemed like it should be 1/3, but the answer is 2/3. You have a 67% chance of rolling a 6 on the first try, given that all your rolls are positive. And that just seems so counterintuitive to me. That's the paradox that I want to experiment with. And I did an R simulation at the end also to look at that. So we're going to calculate it. So let's look at our new sample space. First of all, so sample space 1, if we roll a die until a 6, so we could roll any number over and over and over until we roll a 6. That's sample space 1. But we're taking a sub sample space of that and looking at the ones that are only even. And so that's the sample space we want to look at here. Not sample space 1, but sample space 2, where they're all even. So let's define a T or F as rolled a 2 or a 4, a 6 is rolled a 6, and here's a sample space. N equals 1, we rolled a 6 the first try. N equals 2, we rolled a 2 or a 4, then a 6. N equals 3, we rolled 2 2s or 4s, and then a 6. N equals 4, we rolled 3 2s or 4s, and then a 6, and it just goes on. This is our new sample space. So let's look at the probability of each of these events. So the first one, probability of 6 is 1/6. Probability of n equal 2 is, well, there's 2 2s or 4s out of 6. There's 1/6, so this is the probability that n equals 2. N equals 3, we're going to roll a 2 or 4 twice, and then a 6. N equals 4. So in 2/6 to the third 1/6. That's probably, and it just keeps going. So essentially, we're raising this exponent each event, each additional event. So let's add these up. So we take 1/6, we take this number, this, and let's add them up. In here, let's factor out a 1/6, and then this is a geometric series that has a very specific formula. Do the math, and it's 1/4. So that's the probability of this sub-sample space. Now, what that tells me, if we do the experiment 1 unconditionally, we just roll the die until we get a 6 and do that forever. But now we only want to pluck out the observations where the dice are all even. That's 1/4 of them, only 25%. And actually, that seems a little high to me. So 25% of the original dice experiment, the unconditional, they're all even. Okay, so now let's calculate this. So we're going to use of course, the famous conditional probability statement. Probability A given B is the intersection of, probability of the intersection divided by the probability B. We're going to let n be the number of rolls until a 6. Of course, n can take on 1, 2, 3, 4 forever. And we're going to calculate the probability that the 6 is observed on the nth roll, given that all the rolls are even. So that's this. So it's the intersection, and then we divide by this probability that all rolls are even. Well, this numerator is this x. We're intersecting on all rolls are even. So all the rolls before the 6 have to be a 2 or a 4. And they each have a 2/6 probability. And there's n minus one of them, and then the last roll has to be a 6. Now the probability that all rolls are even, we just calculated that up here, and that's 1/4. And then 1/4 we combine in the 1/6, and we get 4/6. And this is the equation that Math derived for the probability mass function. But when I looked at this, I'm like, that doesn't seem right. And this was the paradox for me, that when n equals 1, there's a 4/6 chance that you roll a 6. That just seems counterintuitive. That's what was paradoxical to me. And that's when I want to show you in a simulation that the simulation results agree with this. Now in Math, he derived the expected value, which means you take the values it can assume times the probability of assuming that summed over all possible values. And so we take this, the probability mass function. And he had a great derivation of this where you take the derivative of a geometric series and then it all falls out. And it's 3/2, as it should be. Now here's my program. I use this package ExtraDisk because it supplies a lot of different distributions that base R doesn't have, and it has a discrete uniform in there. I'm going to conduct this experiment 60,000 times. Unconditional experiment. So I'm going to roll a die until a 6. And just remember that. So some can, any number 1 through 5 and then a 6. So I'm going to track the number of rolls it takes to roll a 6. But I'm also going to track whether all the rolls were even or not. So that I want to look at that. Now this is my loop of rolling you're conducting experiment 60,000 times. And I'll copy and paste all this code into the comments so you can use it and not have to retype it. But now let's look at the mean number of rolls unconditionally, and it's 6, as the geometric series tells us it should be. Of the 60,000 experiments, how many were all even? Well, there was 14,899. That's about 25%, as the theory says it should be. Let's look at the conditional expectation. So we filter on only the even numbers, which are the 14,899. We take the mean, and the mean number of rolls was 1.5, as the theory suggested it should be. But this is the part that I found counterintuitive. I filtered on only even rolls. I tabled the values, and of course I calculated the proportions of them. And the number, in 67% of the time, it was a 1. So it did match the theory. There 22%, we found a 6 in 2 rolls, 7% 3. This is the simulation results. And if we just look at the first 5 probabilities, the theoretical probabilities, 67%, 22%, 7%, 2%, it just matches with the empirical results. Okay, well, that's all I have for this video. Hopefully you enjoyed that. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.